Hello and welcome back to the Hyperthesis episode 99. 99. My name is Feely.
I'm Patrick.
And I'm Liam.
Just a little, what's it called, look back to that TV show Brooklyn Nine-Nine. Eh? I don't know if you guys seen any of it, but it's kind of funny.
Yeah,
it's fantastic.
Yeah, I love that show. I haven't seen all of it, but I've seen like probably every second episode.
All right, so today we don't have any guests today, so we're gonna be just us hanging out talking about interesting things today, which is gonna be on the topic of visualization and how data or theory and such are being presented in science and how do we deal with it. But before we get into that, let's go into the intro topic.
Okay, so for the first time, we have more than one intro topic, which has been a while. But the first thing that's happening, and I'm not the one who wrote this, so if you want to speak about it, you can, but there's a lunar eclipse happening tonight. So if you're listening to this, you definitely missed it. But yeah, we've talked about solar eclipses before, and we kind of had our experience with it before and after. But lunar eclipses are different. They're a little bit more common and a lot wider ranging. And so it's essentially where the Earth is between the sun and the moon. And so the moon is enveloped in the Earth's shadow. So it happens during a full moon, whereas solar eclipses happen during a new moon. And it's a lot wider ranging because the Earth is significantly larger than the moon and significantly closer. So the Earth essentially just blots out the sun. And the lunar eclipse that is happening or happened, depending on if you're from our perspective or an observer's perspective of the podcast, it's happened, and it happened in almost the entirety of the Americas.
So if the sun is blocked out by the Earth, how can you see the moon during a lunar eclipse? I know the answer, but I'm just asking you because you're leading the conversation.
True. So not all of the light is blocked out because the moon is mostly in what's known as the Earth's penumbra. So that's where there's a partial shadow. It's not a full shadow. And part of that, and especially why the moon appears red during a lunar eclipse, is because the sun's still making it through the atmosphere on either side of the Earth, and it's still able to illuminate the moon. It's kind of like when you look at the moon, let's say a first quarter or last quarter moon, you can still see the dark part of the moon, even though, again, it's not illuminated. And then you can also see the illuminated from the sun side of the moon. So it's still illuminated, but it's in the Earth's partial shadow.
Was
that right?
I thought it was something. Maybe I'm wrong. I'm not sure, but now I don't know. I don't trust myself anymore. Now that you've said that, but I always thought it was that the moon is completely in the Earth's shadow. But what happens is that some of the light that enters through the Earth's atmosphere gets refracted and kind of like bends onto the moon, and that's why the moon appears really red. Is because all the other colors of light don't refract enough. Maybe I'm wrong. I don't know.
It's definitely gravitational lensing. No, I'm just
it's like gravitational lensing, but optical. It's just optical lensing with the Earth's atmosphere.
It's just normal lensing with the atmosphere, basically, right? So it's not gravitational at all. The Earth needs to have like much more mass for that gravitational lensing to take effect at that level.
Yeah, but I think we're saying the same thing where it looks red because of the light passing through the atmosphere still, and it's causing refraction. But it just that makes me think of what it would be like to be on the moon during a lunar eclipse, because it would be like watching a sunset, because everything turns red just like in the sunset, except instead of passing through half the atmosphere, the sun is passing through the whole atmosphere. So it'd be, I guess, a very intense, very brief sunset.
Yeah, so I kind of forgot about that, and then I quickly wrote it in the notes here because I'm gonna wake up at like 2 a.m. or something to go look at it. I'm gonna maybe I'll just still be awake then. I don't know, but assuming it's not cloudy, I'm gonna get a good look at it.
Absolutely. Me too.
Well, I think the other ones that I was fortunate to see when I was younger was it's like smiling moon. I know you heard of it. It's like when you have a crescent, but it looks like the mouth, and then Jupiter and Venus becomes the eyes. So it looks like smiling face. It's quite rare. I remember I saw it in when I was home, and it was fascinating because it's like the sky has a little smile. So it's quite rare. Well, maybe it's not that rare. Who knows? But it's kind of funny to see because the little tiny smile, because the crescent kind of acts like the mouth. I don't know if that's happening here, or I don't even know what it's called in English, but in my language, it's more like smiling moon.
You probably need some special alignment to see it, I'd imagine, right? So I don't imagine it's that common. But maybe, who knows? There's a lot of stars out there, so maybe every so often two of them align the right way.
So
Oh, yeah, that's cool.
what's the second intro topic?
Okay. So the second intro topic, aside from a reminder that we'll be too late, is a topic I've been wanting to talk about, but we just haven't had a guest with the right timing coming on the show because we know quite a few people who work with batteries and who have worked with batteries, but couldn't get one on time. And I think it's interesting enough to talk about. So this topic is, for the introduction, is based on a paper titled "The Operation Window of Lithium Iron Phosphate / Graphite Cells Affects Their Lifetimes." This was published by Nico S. Zoldos in August of 2024 in the Journal of the Electrochemical Society, and I've linked it below. Now, you may not recognize Zoldos' name, but you may recognize the name of their supervisor, Jeff Don. In fact, we've had a Jeff Don student on here previously. I'll link that episode too, where we talked about kind of more so solid state batteries, but for Jeff Don's lab, they've had contracts with companies like Tesla, and they're very interested in looking at how the chemistry of batteries can be improved. So this research article was published based on work that was done in the Don lab at Dalhousie University, so close to our hearts in Nova Scotia, and it focuses on what happens for lithium iron phosphate cells that are under different charging conditions. So if you think about charging a cell, and a combination of cells makes up a battery, when you plug your phone in, let's say it's almost dead, the bar is red, it's at like 3%, you charge it all the way up to 100%, and then you use it until it gets down again. So what they're looking at is something similar where they're trying to figure out, okay, what happens to the actual chemistry, what happens to the structure of the cell as it's discharged and charged at different states of charge, or the percentage that it's full, we'll say, and also for different types of battery chemistry. So this paper first came to my attention a little while ago when I was watching a YouTube video from a channel called Engineering Explained, where the presenter discussed some of the results in this paper and a couple other papers, but that presenter, Engineering Explained, tends to focus a lot on vehicles and how they work. I would highly recommend checking them out, and I've linked that video below too.
Do you know how they test what happens when you charge and uncharge the batteries? Because I know it's not very realistic to just plug the battery and let it charge for, a couple hours, then let it sit there and drain for a while. So they're able to test really fast, 10,000 cycles where they charge it and discharge it. And I don't know how quickly it is. If one of our guests was here, they would 100% know, but maybe you know.
I have that just a little bit later on,
okay.
So you're kind of you're teasing a little. So going back, before we get into how they charge and discharge and test these batteries, I do just want to explain what these types of batteries are. And this is something that's very interesting to me just because I drive a battery vehicle and batteries are pretty much everywhere. But there are two main types of batteries that are found in vehicles. Aside from solid state batteries, we wouldn't talk about those right now, but we have the more traditional nickel, cobalt, magnesium chemistries, which uses a combination of those different elements and lithium in the battery. And then there's these lithium iron phosphate batteries, which from the names of it, it just uses iron phosphate and lithium as the lithium carrier instead of these much harder to obtain elements like cobalt. And there's a lot of controversy around cobalt. These LFP batteries, as they're known as, are a lot easier to manufacture and they're a lot cheaper to manufacture. A lot of new electric vehicle companies, especially, are focused on producing LFP batteries. Well, again, solid state batteries are in the works. We'll see when those come out. But cars like Teslas or the Ford Mustang Mach-E's or many of the Chinese brands like BYD, they all use these LFP batteries because they're cheaper, they're easier to manufacture, and they don't have quite the same energy density. So they aren't quite as, you can't pack as much punch in. And they also don't have quite as a high of a discharge current. But again, the cheaper aspect of it well outweighs that. They also have the interesting property that the oxygen contained within the compounds are more locked down in the LFP batteries. So something like thermal runaway, where when you puncture a lithium ion battery, it explodes and you can't put out the fire, that's less likely to happen. So it's safer, more affordable at the expense of less power and less energy density. So that's just a bit of background.
Well, I think there are used for those cases, right? I think in some countries in Asia, they have scooters that are EV, and what they can do is that they have like it's called the batteries can be exchanged. So you go to a station with a bunch of battery, you take it out and switch to a new battery, and that's quite easy when compared to a car have a large battery. It's kind of difficult. But if you're using scooters, and it makes it very basically there's no gas, and if you just be able to make it to the battery station, you don't even need to wait to charge. You just grab a new battery, plug and play, and you just keep it going. So even though it might not have that, if it have enough energy density for like let's say half an hour ride, you do that to work. I think it's still pretty good.
Yeah, and I believe there was one company in Europe. It may have been Renault, but they featured a swappable battery pack for a car where you just kind of go into a station and it just takes yours out, puts another one in. But yeah, so having these batteries be cheaper and more accessible means that you can have more of them. So you can do swapping batteries, or you can, especially if they're cheap enough, you can just put more battery to get the same kind of range for an electric vehicle than you would with these harder to obtain materials and more, or I guess less safe battery chemistries.
How do these batteries? I don't know if they talk about it in the paper, but how do they handle like temperature and stuff? Because that's always a big problem with batteries, and I guess electric vehicles and the scooters, like Feely was saying, is that if you're in countries where it can go to minus 30, it really screws with the batteries. And I guess if it's that cold, there's probably a lot of snow, so maybe. I don't know. Like, I know with scooters, maybe that's a bad example, but with cars, you can still drive cars through the snow, right? So how do electric batteries handle that? I don't know if they talk about it in this paper.
They don't talk about too much. They do talk about the different conditions in which the batteries are tested. So, for example, the main temperature that the batteries are tested at, and we'll get into more of how they're tested, is I believe it's around it's either 40 degrees Celsius or 60 degrees Celsius. So at a decently warm temperature. But that speaks to another point of operating at cold temperatures. Now, I haven't prepared any studies that I've read about this, but just from word of mouth and from speaking to other electric car owners, these LFP batteries are less well equipped for colder temperatures. So the older battery chemistry of the NMC batteries, those nickel, cobalt, manganese, they are easier to charge and they maintain their charge better in colder temperatures than the LFP batteries. And that's something that in Edmonton, I hear about a lot just because it gets quite cold here. Like, for example, my car, when it's just plugged into a 1.5 kilowatt outlet, it doesn't charge under minus 30. So we had to get a new charger installed. But so Whereas LFP batteries, that might be, say, minus 25 or even minus 20. Again, I don't have anything prepared for that, but that does lead into how they actually test these cells. So for the research that was conducted by Zoldos et al., they involved using a specific electrolyte that was, I believe, 2 different types of electrolytes were used, and then they were looking at pre-manufactured lithium iron phosphate packs that had artificial graphite anodes, and they each had a capacity of 240 milliamp hours. So for reference, your phone probably has somewhere between 4,000 and 5,000 milliamp hour battery. So they're quite small, which kind of answers your question, Liam, about how they're able to charge and discharge it so quickly. Because if you want to try and test a battery pack that's used for a car, that's going to take, at the very least, hours to charge and discharge. But all the battery packs in cars, for example, are made out of these just little cells that some are kind of the size of a tall boy, we'll say. Others are even smaller than that. So they're smaller cells that make up these larger batteries. And so by using a very small cell with a small capacity, in this case 240 milliamp hours, you are able to essentially charge and discharge quicker because there's less to charge and discharge.
They must have some kind of specialized way to put like more charge in them quickly than, if I just plugged it in into an outlet at my house, right? Because the outlet at my house has very safe voltages and current levels compared to maybe what you can do in a lab.
Yeah, no, they definitely have very expensive machinery, which I won't get into, but I remember having a former colleague and classmate, I guess, Alex Luley, who gave a talk about his research in the Dawn Lab. And he was saying that they have like a multi-million-dollar machine that's able to monitor the currents going in and out and is able to do what's known as charge cycling. So where it's able to drain and then fill and charge these cells for a certain amount of time under certain conditions. And so it's kind of a very smart device that does this.
Yeah, even like Scott, the guest, our previous guest who worked in the Dawn Lab that you mentioned earlier. I think I remember one time I talked to him after a weekend, and he was telling me that over the weekend he charged and discharged a few batteries like a few thousand times each. And it's like, well, it must be pretty quick, right? Like minutes or something per cycle or less.
Absolutely.
Anyway.
Yeah, and again, these small capacities also help too. So what the researcher Zoldos was able to do was take 16 different configurations of these batteries and then cycle them in this very complex system at different rates for different amounts of time. So the main state of charges, or essentially how much charged the battery is, range between 0% and 25%. So it just kind of cycled between those two. So it would drain it to 0%, charge it up to 25%, repeat. The next one was 75% to 100%, and then finally just a 0% to 100% for kind of a baseline testing for these LFP cells. So I won't get too much into the methodology. I will say that they were able to record a bunch of different things, including the gases produced in the reaction. So these gases are similar to the ones produced, say, in an old phone or laptop. I know MacBooks at one point were really bad for battery swell, and that's just a gas buildup from the side reactions. They also did like an electrolyte analysis post-cycling, X-ray scanning to figure out how the anodes and cathodes have changed, and also an electrochemical impedance. So skipping over all of that, and that's how they're able to determine a lot of the properties of these cells. Their main findings were that the cells that exhibited the least degradation, so in terms of the number of charge cycles, it holds the most amount of charge, say, after 1,000 hours of charging and discharging. It was the 0 to 25% charging range. The 0 to 100% charging range was second, so it showed less degradation. And then the most degradation was actually that 75% to 100% charging. So the findings from this paper indicate that for LFP batteries, having a lower average state of charge is important, and either going from 0 to 100% and then discharging all the way is better for the vehicle than going from like 100% to 75%, then charging back up. So the interesting thing about this is one, the mechanisms. So when these batteries are at a higher state of charge, there's more chemical potential energy that's available. And that means that lithium is more likely to be deposited onto the negative electrode of the negative electrode of the cell through a reduction reaction. And then iron is also actually being deposited. And the higher state of charges mean that this is more likely to happen and these processes are expedited. Now, the very interesting thing is that this goes in contrast with what is recommended by car companies. Because of the nature of how LFP batteries are discharged, it's not quite linear. So for those NMC batteries, it's actually pretty linear in terms of the amount of voltage drop as your state of charge changes. Whereas for these LFP batteries, it's decently linear for a large part of it, but towards the top end of the state of charge, it kind of flattens out. And so what that means is that, let's say between 90% and 100% state of charge, it's essentially the same voltage that's being produced. This means that to try and figure out what your state of charge is for the entire battery system, between that kind of 90 to 100% range, your car has no idea. So it's not really able to calibrate, and then it might give you wrong numbers, meaning that you either have a shorter range appearing in your vehicle or you aren't getting there when you thought you would.
Well, in gas cars, maybe not modern gas cars, but when I was younger, it would say the little dial would go on the empty gas point, and you'd be like, oh no, I have no gas left, but you could still drive anywhere from like 20 to 50 kilometers. Depending on it felt random. There's many times that I think my car was putting in the driveway running on fumes. So it's kind of like the opposite of that.
Yeah. So in this case, because one of the reasons that electric cars don't really have that, when it says zero, it pretty much means zero, is that gas cars have a reserve. So they'll say, oh yeah, we'll count 40 liters in the tank, but the tank's capacity is actually 47 liters. So you do have a reserve built in. Because electric cars have such a short range compared to gas cars, it's getting better. But to try and reserve some of that battery for like, oh yeah, you go under 0% and then you have like 20 more kilometers left, then they're sacrificing range they could otherwise advertise for. So at this point, they don't have it. But the other thing is that these car companies are requiring or requesting that people charge up to 100% so that their systems know that it is actually at 100% state of charge, but that also damages the battery. So I think Tesla, for example, recommends once a week you should charge up to 100% to make sure everything's well calibrated. But at the same time, this causes damage to the battery and decayed range over a quicker amount of time.
Well, modern designers are have much more expertise with planned obsolescence. So, it is what it is. And well, thank you, Patrick, for the enlightening intro story. So we're going to get into the main topic for today that I want to talk about, which is visualization of data. I think it's one thing that we do in science a lot, especially, well, maybe except for some of the physics folks who just, do equations and solve equations. Even some of those to really drive the point might be good to draw certain graph. And Liam draw a lot of stuff, right? So to preface this, I'll get Liam to, I don't know what you want to say.
I want to say, so is written language a form of data visualization?
No. Not in this context. Like, we gotta draw lines at some point, right? If we gotta say a prose is the same as a painting, let's not define painting at all.
If I want to convey data to my friends about what a tree looks like, and I write the tree was tall and brown and had green leaves and had a wide whatever, is that's kind of like I guess you're not drawing. I guess by data visualization you mean like actually like pictures and things like that, right?
Yeah, visual. Yes, by the word. So
Okay,
I want to
but so
preface,
reading words are visual. You read them anyway.
but you can listen to that. It's a recording method, right? Like it's like a podcast. Would you call it visualization if I print out a transcript? Like it's not. Okay. All
Hmm.
right. Anyways, I'm gonna preface this by saying like when people look at visualization of data in daily life, I think a lot of times is misrepresented. So there's a nice part of the poem that I like, and it says, "A truth that's told with bad intent beats all the lies you can invent." I think that's very true because sometimes you see statistics that, let's say you watch the news, it could be anything, right? It could be like stats of, let's say, basketball players or all these stuff. And sometimes you say, like, oh, you a lot of time use like conditional probability or conditional statistics or something like that. And you see, like, oh, okay, this is a shot made further than three pointers percentage and stuff. And but like how much is it translate to winning games? All this stuff. It sounds complicated. I mean, there are people who have degrees in statistical analysis and such. And when you look at the news, sometimes I wonder if people wonder how or why are data presented like this. Sometimes they use pie chart, sometimes they use this block charts or all kind of visualization techniques around, and sometimes it's misrepresented, right? And for example, a company can make the numbers look like, oh, they're broke, they don't have money, they are in deficit, but actually they're picking and choosing certain numbers to make it look like they're not making money. So but because going through the books takes what's called time and require effort for people to do. So when you visualize something, it might not be true. It might be technically true, but it might not represent the truth of the situation. But so in science, so what we're gonna do is gonna be we have to make sure that that actually reflects the results of our experiment or our equations or our solutions.
Yeah, that's exactly what you want in science. And I just googled bad data visualization, and there's all these articles from like snapshots of news um channels. I won't say their names, but showing certain data, and it's like they've really warped the data to look a really particular way, even though it just conveys the completely wrong look as to what it actually is. So it could be a bad like data is very important to convey, but you can kind of do bad things with it to get certain points across if you really wanted to.
Yeah, especially like statistical data, what really important too is like the number of sample points. Let's say if I say 30% of the people disagree, okay, but like if you're asking 10 people and three people disagree. It's like, well, is that enough, right? So I think you have to be really careful when you look at the data. And sometimes a lot of the standard is like you publish the raw, right? Like the raw data is like, okay, this is what it is. And you can do your own analysis and then come to me. And it's like, well, are you telling the truth? Or are you really representing the data in a way it should be represented? Are you, or just to serve your own agenda? And sometimes when you have a large amount of data, it's become very, very difficult to prove that, well, you are doing it in good faith or you're actually doing technically right. So I want to hear, how in science, it seems to be, at least in natural sciences, there seems to be a more objective way to look at things in terms like, okay, these are, let's say, the amount of voltages, right, and amperes. So the laws of physics dictate that certain data have to be presented a certain way compared like the social sciences, which are much more complicated in its number of factors. So there's a lot of things that happen, which we can see from like, let's say, politics, all these things. Like you can see a lot. There's a lot of data, and there are many ways to present them, and misinformation is really easy to create.
I know in like at least physics, what we do, science, that one thing is, like you said, there's a lot of data or there's a lot of stuff to talk about, but maybe you don't have a lot of time, or maybe it's hard to convey a lot of information effectively. So I go to conferences and present stuff there, and it's like I have to present, the last 5 years of my research to a group of people who don't really know about it in 7 minutes or something. So you can't just show them everything you have. You kind of have to do what the politicians and the news companies do and lie to them a little bit in your data visualization, but you have to do it like as honestly as possible. It's like you have to you can't lie. You can't just say like we got the expected result, right? Or else you're just lying and they're going to go read your papers and see that you were lying. But it's like maybe you leave out a little bit of background stuff from the plot. Maybe there's like a little bit of background noise and you just take it away because it's just going to confuse people during your 5 to 7 minute talk. And if someone asks, in your mind and in your papers that was there and you talked about it, but just for like this quick and dirty data visualization, it's like I've had to do that once or twice where I was doing my practice talks with my friends and my boss and just putting in something that didn't really matter, but not for the talk, but did matter for the papers. It just confused the hell out of everyone. So it's like, all right, for the 7 minutes, I have to take it out, and it's in good, like you said, it's in good faith that I'm not sweeping everything or anything that's too important under the rug.
Well, when you said to me, it's like kind of funny. You gotta lie to them, but as honest as possible. Yeah, you
Yes.
gotta lie, but be honest. I think the term should be like you can omit information, right? Like it's like some people
Yeah.
say it's lie by omission, but in a sense, you assume that people have certain background, or you assume that um. So you want to tell them that we assume some axiomatic clauses. Let's say like, okay, if you work on BEC, so I'm not gonna go into the details on how we set up this system, but just just know that we set it up like this. But you want more detail as how we set up, you can ask me later. But for the purpose of this talk, we are gonna assume that this is true. But if you want to prove this is true, you can talk to me later. I think that's a good way to frame it, right? And then you can go into what the result of your experiments or your data is, and without being having to like lie about it.
Yeah. So it's, I guess, like one example of what you just said about BECs is I study one-dimensional BECs a lot. Nothing's one-dimensional, right? Everything is three-dimensional in space. And I'll tell people like, yeah, if you study a one-dimensional Bose-Einstein condensate, then what we found is this, and that's what you'll see. But I'm leaving out the fact that in experiments, people make these. They take the Bose-Einstein condensate, so this ultra cold atomic gas, and they shape it into like the shape of a Cuban cigar. So they call them these cigar-shaped traps. And it's not 1D. And of course, when you do this particular experiment, there's going to be other like uh, effects from your other dimensions and things like that. But within the approximation that this thing's quasi one dimensional, and if you ignore these small other 2 3 dimensional effects, then within that, then that's what you'd see in one dimension. But it's like, I'm not gonna spend 2 minutes describing that during my 7 minute talk. I'm just gonna say in a quasi 1D BEC, this is what you see. And if people ask about it, and then I can tell them, well, I didn't mention this, but this also goes on, stuff I didn't mention. And in papers, it's something you'd have to comment on, probably.
Well, I think one thing that might not just be specific to science, but at least in physics, what we want to keep in mind is that when we want to visualize something, it has to sometimes, I think most of the time, would have to be quantitative, right? Like there are numbers that we have to care about. Like how do you, let's say you have colors in your graph, and what numbers do those colors correspond to? Because it's not just, let's say, oh, I'm putting green here and darker green and lighter green here for just the aesthetics reason, right? Sometimes we want to represent certain greens on the spectra, like, oh, maybe darker green means a lower number, brighter green is higher number. But one of the things that's real that we need to get it right is like, well, what number, right? At what scale are we working on? So if we want to say, you know, white is 0 and black is -2, right? And how we defining the grayscale between black and white. So people who look at our graph or our data or heat mapped or whatnot can not just look at the structure or what the behavior is, but can quantitatively examine our data. Say, oh, it's zero point 0.6 here, 0.7 here. So that's very important in science. So I wonder, Patrick, like because you're doing probably have to deal with a lot of stuff, especially with remote sensing. So how do you, let's say, calibrate or rectify these issues? Because if you have data, large amount of data come in, right, and you want to make sure qualitatively things are consistent, and especially when you plot, people use like techniques like filters and all these stuff to deal with that. Like, how do you deal with visualization?
Yeah, I mean, a lot of the visualizations that are in my field are maps of some sort. And so to have these different types of maps that are representing data, whether real or not, uh, whether it's like an actual RGB image or if it's something that's overlaid on a map, it seems like everyone has their own methodology. And there's been efforts to try and standardize visualization just to make things clear. So, for example, if you have some sort of color map between -1 and 1, is blue going to be -1, ramping up to red as 1 kind of thing? Where, again, there's not a lot of agreements. There's some agencies that are working to standardize, but it's kind of all over the place and it's not always clear in maps, especially in terms of data presentation and when you're dealing with different scales, for example, so looking at a map that's the size of a country versus one that's the size of the city, and trying to include both in the same thing, there's a lot of detail that's lost, and it's hard to um, summarize things and get a good idea of different scales, especially in terms of maps. Otherwise, I mean, one of my pet peeves is the fact that people try and produce global products from remote sensing. So it's like, oh yeah, we remotely sense the whole world. So here's a map showing the biodiversity of the entire world. And it's like, okay, but if you actually read any paper that looks at a local level, like for example, the boreal forest in Canada or any other type, it's like, okay, we can barely tell what kind of biodiversity, for example, is in uh, these areas. So trying to apply the same method, just blanketed across the whole world, it's pointless because there's no meaning unless you kind of break it down. So I get really peeved off at global maps that are like, oh, we did this one specific product, but it's truly a misrepresentation. And most of the time it's like, oh yeah, here's a map of the forests of the world instead of showing like, okay, here's biodiversity because they're related, but it's kind of like a false pretense.
Yeah, I find that like every visualization should have, let's say, a narrative structure or like a point to it. So instead of a lot of time, I used to think that data visualization is just like I'm just showing them the data in a way that's easily accessible. But I think that's just part of it. The other part that's I think is more important is like, what are you trying to tell the audience of that data? Right? Because sometimes you want to put it certain structures or like you want to put a box here to emphasize this is why we are showing you this. And a lot of times in science, the way you can guess that or actually look at what's important is to read the caption. And the caption really tells you like, okay, this is the plot of this versus this, or this is the graph that shows this or that, right? So I'm not really sure that what's going on in the mind sometimes when I make these figures, because as we make the figures, sometimes we realize what's more important to tell, and you write captions like here's what really important.
Okay. So I think it's because I've been marking a lot this week, but I have gripes with captions because a good representation of data should not need a caption. A caption is always useful. When you have figure captions, they're pretty much required to explain the data. But if you've done your job well in actually visualizing the data and labeling everything, then the caption is kind of redundant. That being said, of course, some are important, and sometimes, like captions in a paper, for example, will pull in from different results or parts of the method. So it could be like, oh, yeah, step 5 of the method was used to produce this kind of thing. But a good visualization should not need a caption. And I will stand by that till the day I die. Because if you don't label things correctly, and if you don't have something that has a good amount of detail to inform the reader just by looking at it, you need to go back and redo it.
I think it depends. That's my opinion. But yeah, I pretty much agree that I think that like there's always some way that you can maximize how easy it is to look at a plot or a graph or a picture and understand what's happening without reading anything. But sometimes in these really complicated when really complicated things are happening, you need a caption, and it doesn't need to be like a paragraph of words, but it needs to be like, all right, there's like a box on the in the plot with an A next to it, and and in the caption it says A, this is that, and then B is this, and C is that, and so on. You need like sometimes you need to label things with the caption at the very least, and I don't know. You need to explain things somewhere sometimes, I think. But yeah, I think ideally you can just look at the plot, and within the context of the paper, you kind of know what's going on.
Yeah, I'll agree and disagree slightly too, because well, the way we actually read papers, like well, browse through paper is the first thing I would normally do is go find figures, right? Like I
Yeah,
don't even care about the abstract. The first thing I do, if they have figures, I go find the figures. And because you don't really know much of the context, you just look at the figures like, oh, what's going on? Then you read the caption, and then the caption would tell you the context really. Because if I have to go through the abstract, the introduction of every single paper, I would never get anything done, right? Especially when you have a lot of paper to read. And one of the key things that in papers are figures. If they can clearly show the results in a figure, that's great. So you basically look at a figure, you recognize something that's related to your work, and then you read the caption to provide you the context. So I think captions are critical in providing context and where things are not necessarily explaining what's going on, but they should do that a bit. So like the detailed explanation is going to be in the paper, but the caption can provide the context and what are the actual key results instead of having to go through like the technical text.
yeah, I completely agree with that. It's the same thing for me, Feely. Like I look at a paper, I scroll through, and I see is there any pictures I might recognize, or any like shapes that I'm used to seeing, or what are they plotting, and does it look vaguely similar to what I know? And then once I see that, then I can go like read the abstract and then maybe the introduction if I'm really interested. Then if I'm really interested, I'll read the paper. But it's yeah, like there's nothing. I don't know if this happens to you guys, but there's nothing worse that when I find a paper and I'm like, oh, this looks like it'd be interesting. And I scroll through it, there's no pictures, and that happens a lot because I do theoretical physics. You know, there's a lot of people who will just do like a math paper and there's no pictures, and I do math papers, but I put pictures in them of plots and things to give people context and whatnot. And some of these hardcore mathematician guys, no pictures, and I feel like a child opening a book, and I'm like, there's no pictures. I don't want to read it.
Liam, 2D, hermeticity.
Yeah, I
Remember our
know, but like,
paper?
yeah, we have a paper with no pictures in it, and there's nothing worse than that. I hate it. I tried so hard to think of a way to put a picture in that paper, and I just couldn't justify it in the end because there's like, it's literally just that whole paper is a math proof, which, if you're doing a math proof, then you don't need pictures. And sometimes you do. There's a lot of fields of math where visualization is really important for that kind of stuff. But this is like a pretty, I don't want to say it's a basic math proof because it's a whole paper, but that paper we did is like, it's a math proof, but it's using kind of like simple math. I'll call it that. So, when I'm talking about like physics papers, I guess, I'm going to read a paper about like ocean waves, and they just do a bunch of math with no pictures of ocean waves. I'm like, that's annoying.
Yeah, I think there is humans. We take a lot of information through the eyes, right? And ears and other senses, at least in terms of research level or like to research things, eyes are quite important. And like being able to show your data in a consistent way with the literature, because a lot of times when I was writing a paper and my supervisor was really helpful on this, like, yeah, don't do this, is not what people do in the field, because what we want, especially when you work on a specific field, you want something that people who understand the material or can understand the material or have worked in an adjacent field can look at your visualization. You could look at your figure and know exactly what's going on, or at least know exactly what you work on. And a lot of time when I work in like for in this self assembly and crystal structures, I look at a figure and it's like, oh, exactly, they're working on this. They're doing annealing. They're doing this stimulation. They're doing this, and a lot of times it's quite clear, and it seems to be this unwritten rules and standards you kind of learn from reading literature, from reading papers, and then you realize, oh, this is what I want to adapt into my figures and to how I present my data, or not even just data. It's like the derivatives of data, right? Which are like your analysis of what's going on. Perhaps like, well, this is how people represent dynamical system. Okay, are they really do they usually show snapshots of your system in time, or do people just not don't show that at all and just see the final results? There are so many nuance when you try to visualize things that perhaps like when you go to, let's say, conferences, some people do some whack stuff, right? Like, and looks beautiful, but sometimes you just so captured by the form and not the content. And I think what I learned over the years is that, before I really like to make things pretty because it's nice to look at, but sometimes it's better to just make something very standard, something that everybody sees all the time. So it doesn't invoke the sense of like I have to try use my brain, part of my brain, to try to make sense of this new beautiful format. But I just want to look at the same old format I have seen, so I can focus on the content of your, let's say, poster. So I think there's an argument there, but I don't know where the balance is. Should you go for something that's like really pretty and you know novel, the news is gripping to the reader, or just do the same old stuff? Because what's more important, like wearing a uniform, what's more important is what you say in that poster. Is more important. What's more important is like what your actual results.
I think it depends on your audience, right? Like that's usually the case. If you're presenting to all these people directly in your field, you can probably just make a really simple plot um, that conveys the information really directly and efficiently. You don't need to like do its makeup. But if you're presenting to the public, then you might want to strike this balance between effective yet nice looking. And I don't know, like when I read papers and they have really nice looking figures, like I don't know, the papers feel better. I don't know how to describe it. So I think you want to try and make it as nice looking as possible, but without losing the gist of what you're trying to say.
Yeah, I think. Well, the was the first question when you want to communicate anything, be it talking, be it painting, visualization, all this stuff. The first question you should ask is who's the audience, right? Like who's
Yeah.
listening, who's seeing this thing, and sometimes like if I want to present my work to, let's say, 10 years group of 10 years olds, then I'm not gonna doing the same thing as like I might not even put any equations in. I just might be a bunch of doodles, right? So things can be very extremely different, like vastly different, depends on the audience. And sometimes we are stuck in this idea that we want to just present to experts, and sometimes we forget that, like, well, sometimes it might be good to goes back to something simple. I know that like my supervisor, when he teach classes, he, instead of like fancy figures, he just doodles. He has like figures that are doodles. Like this is what how thermodynamics work. Has this little guy move this little guy. It's like, well, it's kind of a little funny, little doodles, right? But I think it's really relatable because like it brings back to something that people are used to. It's like, oh yeah, it's just this little boat is moving this little part of another boat, and this is like thermodynamics.
One thing I think that's worth mentioning is that like technologies really helped with data visualization, right? Because papers that were written 100 years ago, they didn't have all these fancy programs that could plot fun shapes in 3 dimensions. Like, just imagine like the orbitals of atoms, right? You get these wild quantum mechanical shapes and things, and trying to draw those by hand. I think it's doable, but maybe not every single person can do it, and it's easier to see in some of these fancy software plots. So I think even like I go and read old papers fairly often, and most of the plots are just like the author like doodled something, like you said, and that usually does a good job. But sometimes you need something a bit more sophisticated to get the point across, especially when you're dealing with things that aren't in one dimension.
Yeah, which brings me to like the next big topic that I want to talk about. This is inspired by an event at Queens here is called the Astronomy on Tap, which is at the bar where astronomers do an outreach basically, and they talk about astronomy with different topics. Sometimes there's like a debate between two astronomers, or this event is kind of fun. And every time they have they have trivia, and also the other part is kind of quiz-ish. I don't know what to call it, but they show 10 pictures, 10 images, and you have to guess if it's nature, simulation, or imagination. And sometimes it get really difficult because like, is it nature or is it a simulation? Usually the artist's imagination, things are quite obvious, and sometimes it's not, especially when you look at astronomical photographs or like images. Like, is it a simulation or did the new James Webb take this because they're really beautiful? Is it even real? So I want to talk a lot about it a bit because sometimes when you look at scientific figures, usually if you read a caption, it will have to tell you if this is an image from a real experiment, or if it's a simulation, or is it just some the author just draw this up to, let's say, to produce or to replicate what the behavior of this looks like, but maybe they don't have the simulation or the real data, right? So what I do sometimes when in my papers, like, oh, I'm just drawing how the particle works, and this is like what it should be, but it's not really the image of a simulation, but it tells you the behavior, because it's really hard to show if I want to show like things that let's say self-assembling or stuff. We wish you can show it, but if you want to understand like how forces work, it might be nice to just like take out a particle or draw it and draw forces all around it. And it's like, oh, this is the direction it goes. But in a sense, I'm adding something that's not my simulation in it. It's basically my imagination to represent what the force looks like. And sometimes you have to be very precise. It's like, no, no, it's the angle has to be this exact angle to make it true. Or sometimes I'm just making this doodle to show you the behavior of it instead.
Yeah, I like these qualitative plots is what I'll call them, because they get the point across. And like, so for example, in one of my papers, I wanted to make a plot of the trajectories of these particles in space, like the phase space diagrams. So position versus momentum plots, right? Tells you the trajectories of the particles. But it really, the trajectories depend on your initial conditions, and they depend on kind of different parameters. And I don't want to have to plot. I didn't want to plot like 20 different plots that look similar for different sets of parameters. So I just, in the plot, it's like, if for some range of parameters, it should look something like this. It'll warp a little, it might change a tiny bit, but you'll get this overall shape to it. And I find those qualitative plots are kind of helpful because, like, when I'm explaining physics to undergrads, I don't, if I'm trying to explain some free body diagram, I normally don't explain everything super specific to them, and I don't use exact angles and exact forces and stuff because it's up to them to do the question. I'm just trying to get like, here's the picture, and then you can do the math on your own.
So during like if you start in my group, there we have like one of the quote unquote training meetings and such. And one thing that my supervisor would show is this like visualization and making figures. And we basically, or he basically break down images or figures into three groups: data, knowledge, and understanding. So data, sometimes you see a figure that's literally just an image of their experiment, or image of what's happening in their, let's say, what photograph they have of the experiment, right? Like, oh, here's what's going on. This is just data. And you have something that's more like knowledge. So it might be an image of your experiment, but there are arrows pointing into it. It's like, okay, we know this thing is here, this color is this color. And then you have another type, which is understanding. Maybe they're not even an image of the experiment itself, but it's like the mock-up of the particles. And then, oh, it goes into this part of the experiment because this happened. There are forces that goes into this. These are the potential well that this supposedly particle live in, right? So I think it's nice to see that you can break down complicated figures into like, oh no, this part of the figure just telling you data, and this part providing you knowledge, and really the bottom part is like, well, why does those knowledge happen? Because it's usually how we look at like how we understand things. We should have, at least in your paper, you should have something that provide understanding, right? At least the point. If it's not, it's just gonna be, let's say you just publish the tables of data. It's kind of not very useful. So I wonder, like when I'm gonna be writing paper soon, or technically I'm saying writing ish now, like the process that we make figures are not exactly linear, because like it's not like, here's what we want to say, oh, this is exactly plots I want to make. And what I find that the process when I make figures, or the visualization process, I don't know what I want to say. And by making the figures, by making visualization, I start to understand more of what I want to say. So I evolve my figure to represent what I want to say. It's like writing too. I don't know if you guys experience similar things where I don't know what I want to say. I don't know what the crux of the take home message I want to give it to people. But as I start writing, I discover that, well, maybe I want to say this, I want to say that. Even though I have my results, it's like this happened, this happened. But the way I want to present things evolve along the process. That's why we have like first draft, second draft, third draft, and we revise and revise thing. I think that process is the same, or not the same, but or very similar when you make figures. You make bunch of stuff that point to saying, here's the understanding we want to give, but then I look at it, oh, maybe is it right? Like, is it really, do I understand it? Is it what really I'm saying? I think there's a lot of repetitive process of revisions.
Yeah, well, it's like as you write the paper, you kind of learn more about it, and revise things. It's the same with the figures. You initially were thinking of your data that you were plotting in a certain way, and then you make the figures to convey the information and whatnot. But then maybe like a couple weeks later, you're thinking of it in a slightly different, better way, like a better way to describe it, or a more um, physically realistic way, or something like that. And so maybe you change your figure to reflect that. I think that's like pretty. I think that's just part of the process, right?
Yeah, I was thinking too, like, I don't know if you use, I know, Liam, you do all this, what's called theoretical stuff, right? Even though you do a bit of simulation, I don't know if you even do simulation for stuff. But when you do like theoretical solutions, for example, I remember you were having some, it's not doodles, it's like some lines going here and there to show the path of the solution and stuff, right? Like, and people what would you call it? Is it standard? Like, is are they usually standard way to visualize something that abstract? Like, I remember you were doing something with acoustic black holes, like this, how the system behave in this loop, going to the next one, next solution.
Yeah, that was kind of a non-standard way to do things, but the whole point was that in that work, you took something that was standard and you changed it, and then so you're making it more uncomfortable for people to look at. But so you're losing that, but you're gaining something else that isn't in the standard way to visualize that data. Um, you're gaining the fact that you can now see. I mean, we'd have to talk more about that method, but you're gaining something and losing something. So it's kind of like a give and take. But yeah, like there is a lot of standard ways for data visualization. I know, like in that work, we were calculating asymptotics, which is just a fancy way of saying you have some really complicated math function, and you can make it look, you can approximate it far away from something. So the analogy I like to use is that a piece of broccoli is an asymptotic approximation of a tree, because very far away a tree looks like a piece of broccoli, but when you get closer to it, there's bark and bugs on it and individual leaves, and it has roots, so it's obviously not a broccoli. But very far away, it looks like this much simpler piece of broccoli. But anyway, the point is that in that field, in asymptotics, to calculate asymptotics, you have to use the complex plane sometimes, and there's these like standard, they're called steepest descent diagrams that you plot in the complex plane, and I'm not going to get into them, but it's like a standard way to find the asymptotics of these complicated functions. And what we did was we took those steepest descent diagrams, and we kind of like, they're these infinitely spiraling loops, and we unfolded all the loops into a single plane. So you lose the fact that now people look at it and they're a bit confused, because normally you just look at these diagrams and they look a certain way. But now you gain the fact that you can see what's happening on each of these, on the whole sheet. Instead of having to think in 3 dimensions, you can now think in 2 dimensions.
So those graphs for you, are they, what do you call it? Reality, simulation, or imagination?
Well, they were like analytic, so they're reality in some sense, but the reality in a sense that it's a simplified theory, right? So it's real, but it's neglecting a lot of background things. It's neglecting. I can't really get into it without talking about it for too much longer. And for the sake of time, I probably shouldn't.
Yeah. It's an approximation of reality.
Yeah,
Of like,
that's what it. Yep, I would say so. And I am doing simulations right now. Actually, I got some nice code recently from one of our previous guests, Wyatt. So he worked with my supervisor, and he sent us some very nice code about solving, basically simulating Bose-Einstein condensates in 3 dimensions. So I've been doing a little bit of code with Python that some undergrads who work for Duncan developed, and I've been using that. So I'm not like a coding expert, but this code Wyatt sent us is just crazy good. You can do it in 3 dimensions. You can kind of do whatever you want to the BEC. But again, even those simulations, they're an approximation of reality, because they don't account for every single thing that's happening in a BEC. They just account for like the dominant things at very low temperature.
yeah, I would say that, well, simulation, yes, is an approximated reality, right? But I think for the sake of this argument, like reality is just like you take data from, like, you capture it from something. You have a sensor, you're sensing directly or indirectly. I would say that's data. That's like of reality. But a lot of times when we solve equations, we have to neglect certain things to make things work. And lots my simulation like is really just there's not no air or nothing. And sometimes, most of the time, there's really good reason for that, right? Let's say like the magnitude of the influence of those things literally is just negligible. It doesn't change anything. But when you go to different system, maybe the medium in which you're simulating in matters. Like let's say you work in colloids or depletants and stuff and dimers, all these things, there are entire other fields of how you simulate things where there are little things that affect your system. So yeah,
Yeah, if you're gonna like describe throwing a ball through the air, you'll use Newton's laws or something, right? But maybe you can ignore air resistance. Well, if you're trying to describe sound waves, like you need a medium for them. So yeah, depends what you're doing.
well, I think we have pretty good discussion on visualization. I think is went off everywhere like fireworks, just go all over the place, lighting up different fields. But I think the crux of it is in scientific literature, visualization is a tool that quite crucial, especially when you try to tell a story or tell your result in a very succinct way. If you can make a figure that tells your story, that's gonna help your paper a lot, especially now when you look into a lot of reputable journals. They're gonna have highlights, right? Like this paper talk about this, and some paper actually ask you to have one figure that shows the result, and maybe a big figure with multiple panels and parts to tell you like, hey, when a reader comes, they should be able to see this figure and know what you do. So apart from that, and or in addition to that, science we requires precision in the quantitative domain too, where it's like, well, not only you have to have this understanding, show arrows here and there. Most of the time, when you work with something with simulation or reality, you have to make sure people can like either replicate that or understand the scale at which you are working in. So it's a quite complicated thing, and that's why I think we are doing graduate school and PhDs and stuff to figure out the nuance, all this and such. Well, that was great. So we're gonna move on to the story, but before that, I'm gonna get Patrick to tell us how to reach us, and then we get to the story.
Absolutely. So, if you would like to reach out to us, whether you have input on data visualization and ideas on how it can be better done or better displayed, or if you have opinions on this matter or any of the other topics we've discussed in this episode or any episode, you can reach out to us through email. We are hyperthesispodcast@gmail.com, or you can send us a DM on Instagram. We are at the Hyperthesis on Instagram, and we also post updates and some fun pictures, especially of our guests and their work on our Instagram page. I don't have Instagram personally, but I get informed by my significant other about different posts, including our, at the time of recording, most recent post, I think, celebrating all of our female guests on the show for International Women's Day. And maybe, who knows, by the time you're hearing this, you'll see a picture or two of the lunar eclipse, depending if conditions are correct. If you are listening to us, congratulations, you found us. We are based out of Spotify, but you can find us on pretty much whatever podcasting service you use, including Apple Podcast, YouTube Music, Audible, wherever you find your podcasts. We are also on YouTube. You can listen all the way up to our last season on YouTube. We have some fun visualizations that are unfortunately very intensive to process. So maybe one day we'll get caught up with this current season, but we like to give our computers a break or use them for research every now and again. So whether you want to suggest new topics, or if you'd like to ask questions, leave comments, or if you would like to be a guest on our show, we would love to hear from you through whatever means necessary, whether that's sending us a DM, sending us an email, giving us a rating and a comments and feedback and everything in whatever podcasting service you may use. Regardless, reach out to us. Let us know what you like. Let us know if you'd like to be a guest. And keep an eye on our social media posts, as we are one episode away from episode 100, which we are very excited for.
All right. Thank you, Patrick. And now we have the story from Liam.
All right. So I thought today's episode was going to be a bit more simulation-based discussion. Simulation and data visualization are definitely highly connected. But today's story is on the history of simulations in science. So whether it be, you're solving simplified things, so my version of a simulation, which is like numerically solving differential equations, or whether it's like a proper real simulation where you're accounting for different forces and different interactions. Simulation, or whether or not it's, a statistics kind of thing, or you're doing random numbers and simulating things with those. Simulation's super important in the world today and in science. So I found a paper titled A Brief History of Simulation that was published in the Proceedings of the Proceedings of the 2009 Winter Simulation Conference by David Goldsman and others. The paper gives a brief history of simulation from 1777 to 1981 in a very kind of informal way, and it highlights specific people, places, and events that furthered our development of simulations, and it focuses on discrete event simulations and Monte Carlo simulations, which are two very popular methods used even today. So I'm going to try and quickly summarize that paper. So the history of simulation can be written from different perspectives based on the different types of simulations, based on the programming languages that are used, and based on the communities and the fields of interest that apply the simulation. So they can be applied in manufacturing and theoretical physics, the military, weather, and so on. So starting with the pre-computer era, so 1777 to 1945, a big one, the Monte Carlo simulation, a big type of simulation, as we now know it, was generally considered to have originated with the Buffin-Laplace needle experiment in 1777. The experiment involved throwing needles, like these little sewing needles, onto a flat plane, and this flat plane had equally spaced parallel lines drawn on it. And somehow you can use that to estimate the value of pi using statistics. So I didn't have time to go look into this experiment, but I think it's something you can Google or YouTube, and there's people talking about it.
Well, I think the easy way to explain Monte Carlo simulation is like, well, if you have a pawn, right, and you want to know what's the area of the pawn, so you can grab a rock and just randomly throw around the rock and see how many times you hear the splashing sound compared to how many times you throw the rocks, and you know the surface area of the rock, so you can estimate how
Mm,
big the pond is. I think it's the same way in your setup, but it's the fact that, well, I think your setup just turn out that what you get is pi, always pi, because the way the area works, it just turn out the area is pi.
yeah.
Right?
So
It's
some
a unit circle. If it's a unit circle, the area is pi. So if you throw the needles enough, you know, it's like, oh, yeah, yeah, this amount of needles that we can hear or what's it called, observe is going to be around pi.
mhm. Yeah, so that was like the first version of the this pond thought experiment where with needles though. So that was in 1777, right? So that was a long time ago. That's kind of the first known Monte Carlo like thing that people have done. So Buffin published the solution to this, but it had an error that was corrected by Laplace in 1812, hence its name. In 1899, at the age of 23, William Gossett, a mathematician and chemist, became a brewer with Arthur Guinness, Son and Co. Ltd. Guinness allowed Gossett, so Guinness, like, the beer, Guinness allowed Gossett to publish certain statistical results that the company obtained in their kind of industry manufacturing, provided he used a false name and no proprietary data was used. So he chose the name Student beginning in 1908 and published a paper formulating what is now known as the student T distribution. Gossett compared analytical results against manual simulation. So I guess manual simulation is like you're calculating things. I don't actually 100% know what that means, but he used manual simulation to verify that his T distribution was correct, or his conjecture was correct. And it's pretty cool that this application of simulation to the industrial production of beer was a major stepping stone for seeing how useful simulations could be. So, it was like it was one of these rare instances where a long time ago they used it for something realistic right away. Like Newton's laws, when he was developing them in, his attic or his place at Cambridge or wherever he was. I don't know if he necessarily was doing it to try and optimize production lines and things like that, right? So it's interesting how that came to be. But after this period of 1777 to 1945 came the formative period from 1945 to 1970, based on this paper I was reading. The invention of general purpose electronic computers allowed for the practical application of Monte Carlo method. Um, And the Monte Carlo method was actually named and coined by Stanislaw Ulam, if I'm pronouncing that correctly. So Ulam, he was one of the primary developers of the Monte Carlo method, kind of like the modern day version of it. And along with he named it after as some people probably know, he named the Monte Carlo method after the Monte Carlo casino in Monaco, and he was inspired by his uncle's gambling habits, apparently. So don't say gambling never did anything useful, I guess. So Ulam, along with others like John von Neumann, used the Monte Carlo method technique to solve complex problems like neutron diffusion which was applied to develop the hydrogen bomb during the Manhattan Project. So that's pretty wild. The Manhattan Project was apparently a very big time for the development of simulations. And the fast progress on computers allowed for other simulation techniques to develop alongside this. So Keith Tocher developed his development of the general simulation program and contributions to simulation methodology, including the three-phase method for timing executives and the creation of the activity cycle diagram. These things were all very instrumental in simulation theory. Now, I fully admit I don't know what half of this means. I'm a theorist, but I know Monte Carlo. Meanwhile, during this time, Geoffrey Gordon's introduction to the general purpose simulation system at IBM revolutionized simulation modeling for complex systems, and there were various other notable developments. This formative period of simulation also saw foundational work in simulation theory. I'm just going to skip some of that because I don't think it's very interesting anymore. But this leads to the expansion period from 1970 to 1981, which saw the development of enhanced modeling tools like discrete event computer simulation modeling languages, methodology for object-oriented model development, specialty simulation procedures for niche markets, maybe Bose-Einstein condensation, and contributions to formal verification and validation. Advances with respect to analytical research also took place. Kind of like the analytic theory behind simulations. Going beyond the expansion period, this next information is not actually from the paper because the paper only goes up to 1981, but going beyond this, from 1982 to the early 2000s, the development of more powerful and accessible computers again allowed for increasingly complex simulations. For example, in the 1980s and 1990s, simulation was used extensively in fields like manufacturing, healthcare, transportation, and military planning. And additionally, the 1990s saw the emergence of new areas of simulation, including computer-generated visualizations in academic fields, as well as fields like things like video games, film production, and virtual reality. Simulations were used to do things there. Even, recently, pseudo-recently in Interstellar, the movie, they used simulations to create the most realistic black hole they could. And as one thing that happened during this early 2000s was that as computational power increased, so did the capacity for simulations. That's kind of the take-home message. And even really complicated things like large-scale phenomena and weather patterns to economic systems, things that are very complex, they're able to do simulations for now. From the early 2000s to present day, these computer simulations have become so deeply embedded in science and industry and daily life, they're extremely important. The development of high-performance computing, cloud computing, parallel processing, all this has allowed for the simulation of very complex, highly detailed systems in real time, such as climate modeling, financial market simulations, complex engineering design, and the kind of, I don't want to say invention, but the recent developments in artificial intelligence and machine learning further revolutionized all of this. As of 2025, simulation just played such a huge role in our life today. Needless to say that it's one of these crazy important things humanity's come up with during our lifetime. So that's it for me.
Thank you, Liam, for the story. And for next time, we will have the 100, the centennial, right? It's the century episode of our podcast. So stay tuned to see what's going to happen. Take care.
I think that'll be a really fun one. See ya, everybody.
Bye, everyone.